Okay, now another set of reactions that result in the synthesis of alcohols are another type of reductions. However, we're not using a hydride source in this case. We're going to use Grignard reagents. You've done this in laboratory, actually. You took benzophenone, a carbonyl-containing compound. You reacted it with a Grignard reagent, magnesium bromobenzene, and you resulted in triphenylmethanol. Remember, that was the whole point of the lab, was to synthesize triphenylmethanol, and you confirmed it via IR. So it seems complicated using Grignard reagents, but really it's the same process that we've just talked about, where we used hydrides instead of Grignard reagents. We've got some nucleophile that attacks a carbonyl. We form our light bulb, alkoxide. We can reform that carbonyl if we have an ester or a carboxylic acid, or we can just go ahead and protonate it to form our final alcohol. Instead of a hydride, we're just going to substitute, a Grignard reagent here. So let's look at that now. Let's give an example. So let's take, let's do this, a simple carbonyl-containing compound. Let's be very simple about it and take formaldehyde, right? And let's react it with a Grignard reagent. Let's take, let's say, bromocyclohexane. We'll react it with magnesium solid to generate our Grignard reagent. Remember doing this in lab? You ground up your magnesium, put it in with your alkyl halide, and you generated this coffee-colored, in your case it was phenyl magnesium bromide, coffee-covered Grignard reagent. We were real careful about this. We didn't want any water in our reaction because this reactive Grignard reagent is very reactive. It would even react with water instead of reacting with our carbonyl. But when we thought of our Grignard reagent, we said, well, it's a very interesting organometallic reagent. It's very useful. And we can think of it as almost like a salt. Our magnesium we think of as 2+. Our bromine we think of as 1-. And really this alpha carbon, the one directly attached to the magnesium, has electrons sort of pushed onto it by the metal. So we think of that carbon, alpha carbon, as having a 1- charge. Okay, and a lot of times I like to really think of it as a salt, right? I think of it as if that alpha carbon has a lone pair and a negatively charged carbon, a carbanion. And like a salt, it's counterbalanced by these other ions. That's a plus, Br-. But this is really our nucleophile. And we can treat this carbon chain and this carbanion almost like we did a hydride when it reacts with carbonyl-containing compounds. Here's our nucleophile. Here's our electrophile. Delta plus, delta minus. And we are going to generate an alkoxide intermediate, just like we did when we attacked these carbonyls with hydrides. Negatively charged alkoxide. In this case, our nucleophile isn't a hydride. We're making a new carbon-carbon bond. These electrons from our carbanion, our Grignard reagent, are going to be used to form this bond right here between that alpha carbon and the carbonyl carbon. So we're bringing along, in this case, a cyclohexane ring. Okay. Now, the mechanism is the same, right? The generation of the Grignard reagent is something a little different, but it results in a nucleophile that can react with a carbonyl-containing compound to form this alkoxide. Hopefully when you see this alkoxide by now, you're like, whoa, okay, I have to think about something. Can this alkoxide reform the carbonyl? Can these electrons come back in to form that carbon-oxygen double bond? The answer to that is, do you have a leaving group? No, not a good leaving group, not a leaving group, not a good leaving group. So we're sort of done here, like we were with aldehydes and ketones, is that alkoxide in the presence of acid will become protonated. CH2OH. And that's our final product for that reaction of a carbonyl-containing compound with Grignard reagents. It's still a reduction, right? We have less carbon-oxygen bonds in our alcohol product than we did in our carbonyl-containing reagent. And it's another way to synthesize alcohols. It's a more complicated way because not only are we reducing the number of carbon-oxygen bonds, but potentially we're bringing along other carbons with our Grignard reagent. That can be very useful. Okay. Now, just like with hydrides, we have to consider two-step reductions with things like carboxylic acids. Here's our acetic acid again. Let's react it with a simple, let's do not so simple, a Grignard reagent here. Okay. Again, you have to remember which is the alpha carbon. Here's our alpha carbon. This is the one that's going to be very nucleophilic. We'll react with that alpha or with the carbonyl carbon to generate our alkoxide intermediate. It's going to bring along CH2, CH3. Right, this negative charge is going to be counterbalanced by Mg2 plus, Br minus. This was the adduct. We called this an adduct when we were doing the laboratory, salt adduct, and we protonated it. Remember, you got the pH paper out and made sure that your pH was decreasing. But here's our alkoxide, negatively charged. Boing, light bulb. Can this reform? The answer here is yes. We've got a potential leaving group. This OH can be turned into water in the presence of acid, and so just like we saw with hydrides, we can break this carbon-oxygen bond to reform carbonyl. And water will leave. Right? Since we've reformed this carbonyl, we have an opportunity for a two-step reduction with another dose of our Grignard reagent. Right? Boing, boing, to generate our second alkoxide intermediate. Here's the first ethyl group that we attached in the first step. Here's the second ethyl group that we've attached in the second step. Alkoxide intermediate, can it reform a carbonyl? No. Bad leaving group, bad leaving group, bad leaving group. So we finish the reaction through a simple protonation of that oxygen. And in this case, our final product let me just put this in parentheses, is a tertiary alcohol. Same process that we saw with hydrides. It's just instead of a hydride, just a hydrogen, we can bring along a carbon chain, right? A cyclohexyl group, ethyl group, but we always have to consider that alkoxide intermediate and determine whether we can reform the carbonyl and have a two-step synthesis of an alcohol or one step. And again, even though we're not adding carbon-hydrogen bonds here, these are still reduction reactions because we're reducing the number of carbon-oxygen bonds. 2 carbon-oxygen bonds to 1 in the alcohol, 3 carbon-oxygen bonds with a carboxylic acid or an ester. The first step reduces it to 2 carbon-oxygen bonds to form a ketone. And the second step reduces it even further, 1 carbon-oxygen bond in the final alcohol group.